Welcome to Easy Math TV. We're going to continue our video series in statistics, and this time we're going to talk about the central limit theorem. I haven't even given a definition of that or stated what it is, but let's just discover it along the way. That's the whole idea of this video, is that we're going to just see it in action and try to understand what it's all about and how it's useful, like what can we take away from it. So we're going to be starting with a given distribution. So in this case, I'm going to just move this down slightly. You can see in front of you a histogram of a population X. So this is a random variable X that has, in this case, it's a skewed population, but we really don't know what the distribution is called or what it actually is. It looks skewed to me, but oh well. And we know that the mean, which is mu, is 8.00, and we know that the standard deviation sigma is 6.22. So in this case, we have to know those two things about the original population in order to just be able to simulate the central limit theorem. In the future, though, we'll be able to just use the central limit theorem. We're going to assume that it's true. And so all we will know about is the sample itself, and that we'll be able to go backwards from the sample to talking about what that population is all about, that it came from. Okay, so basically this gets us kind of in gear or in the proper mood or the proper position so that we can enter into an area of statistics called inferential statistics, where we're going to be asking ourselves, what does the data tell us about the population? Instead of just looking at the data itself and trying to understand what the data is saying, we want to also understand what the original population is that data came from. Okay. And so our population data is given to us here, what I just said. And then we're going to be taking samples of size 10 from that population. Okay. So we're starting with a population and we're taking samples of size 10. And our two goals are, we're going to observe how the sample mean, not the population mean, but the sample mean is going to be normally distributed. And then we're going to also observe and record information about that, the distribution of the sample means. So we're going to take a bunch of sample means and look at that distribution. And what do we know about it? What can we calculate its mean? Can we calculate its standard deviation? And what's the relationship between that and the original population, if any? So, because there isn't necessarily a relationship between the sample means and the original population, but we did discover that the central limit theorem claims that there is. Okay? The central limit theorem claims that there is a relationship. So, using this website, let's go ahead and take a sample. So I'm going to click on the word animate, and there's a sample of size 10 from the population. And look, on the third graph, right on the second graph, we see the x's, and on the third graph, we see the value of x bar. Okay, that's the sample mean. So the x's themselves are distributed here in the second graph. We have the heights tell us like how many x's there were in each of these bins. So the first bin was between 1 and 2, and there were 2 values of x between 1 and 2. The second bin was between 1 and 2. There was 1 there. There was 1 x between 2 and 3. There were 3 x's between 3 and 4. There was 1 x between 5 and 6, an x between 7 and 8, and an x between 8 and 9. So if you look at the heights of these rectangles, they should add up to 10. 2, 3, 4, 5, 6, 7, 8, 9, 10. So each of those rectangles heights should add up to 10. All right, that's our first sample. And our first sample mean was a number between, looks like between 4 and 5, if I'm not mistaken. 1, 2, 3, 4, yeah. Somewhere between 4 and 5 was our first sample mean. Okay, so hopefully that made sense. We were pulling numbers down from the top distribution. We were taking our values of x from that, plotting them here in the second graph, and then we calculate the mean and we plot that here on the third graph. So let's do it one more time. So there's our x's appearing, and there's going to be 10 of them all together. All right, so there's our 10 x's, and then we calculate the mean of that and we plot it down here on this graph. So in addition to the value between 4 and 5, we now have a value between 5 and 6. Okay, there was a mean between 4 and 5, and there was a mean between 5 and 6. That's interesting. Okay, let's do it one more time. Here's another sample of size 10. And each time we do this, they could look very, very different from each other, because the original population distribution goes anywhere from 0 all the way up to 32. It's just that the numbers at the high end don't occur quite as often. So every once in a while, one of those will show up. So you can see here that we actually have a number that's kind of in the high end of the scale, but most of the numbers are going to be down here in the lower end of the scale of the values of x. But these are pretty spread out. So, so the standard deviation of that sample is going to be pretty big, of that particular sample. But here's our 3 sample means now. So in addition to the one between 4 and 5, the one between 5 and 6, we now have one up here between 7, 8, 9, and 10. So this sample mean had a value between 9 and 10. Okay, so it was pulled to the right a little bit because of that outlier up there at the right. So let's take another sample. This is the reason why we need to take multiple samples, because of these random chance events. Sometimes you're going to get weird things happen, and that can happen occasionally, but we want to factor those out. We want to make sure that those do not have an oversized impact on our overall view of what the sample means are going to look like. So every time I hit animate, we're going to get another sample, and we calculate another sample mean, and we're going to be building on this histogram down here in the blue. The blue histogram is just going to continue to be built on. Every time we take another sample, we get another value of x bar to add to our histogram there. And so, the more x bars we get, the more we will fill that in and be able to eventually see what the distribution of x bar really looks like. What should the distribution of x bar really look like? So every time we take a sample of size 10, every single time we're calculating its mean, the mean of that sample, and we are recording it down here in this third graph. Okay, so right now we have about 12, 13, let's go up to 15. I just want to see what happens if we get to 15. So we're still really not getting a pretty picture of what the distribution of x bar looks like. So good thing we have software, because the software can repeat this simulation over and over and over again, just like that, in the blink of an eye. So I'm going to hit 100,000 and see what happens. to our X bars. So if you may not be able to see these numbers really well, but on the left of our histogram, the tallest rectangle is at 18,804. 18,804 sample means, X bars, were at that tallest rectangle. And it looks like that's, let's see, 1, 2, 3, 4, 5, 6, 7, 8. So that's between 8 and 9. Okay? The tallest rectangle is between 8 and 9, which is interesting. That would tell us what the median is. But the mean and the median are both 8.00, which is kind of what we were expecting. So you can also see that the histogram is kind of symmetric. It's symmetrical, and it is tallest in the center, and then it tapers off to both sides, which tells us that this distribution is bell-shaped. It is normal. So the central limit theorem, that's what the central limit theorem is all about. The central limit theorem says that the sampling mean, which is our X bars, X bar is the same as our population mean. So X bar is 8.00, and the original population mean was also 8.00. So whenever we take a sample from this population, we can be fairly confident that the mean of that sample represents the mean of the population in some way. Okay, within a certain margin of error, right? Because there's always going to be a margin of error. You can't always get it exactly. Each individual sample you saw did not get us a mean of 8.00. But over time, when you take 100,000 samples, you get a mean of 8.00. The second observation is that the standard deviation of those X bars, which we calculated here, so the standard deviation of all of these numbers, so remember we took 100,015 samples of size 10. So that means we have 100,015 values of X bar, right? That's our data. Our data has 100,015 values of X bar, right? And so when you calculate the standard deviation of that data, you get 1.97. So I wrote that number down. And according to the central limit theorem, that should equal our population standard deviation, which was 6.22, divided by the square root of our sample size, which was 10. So sigma divided by the square root of n should equal 1.97 if the central limit theorem is true. So let's check that. So we're going to have 6.22, and I'm going to divide that by the square root of 10. And the way I have to do that on this calculator is I have to type in the 10 first and then hit the square root key. So that's the square root of 10, and I'm going to hit equals. So 6.22 divided by the square root of 10 was 1.9669367 and more decimal values. So it's not an exact number, but if we round it to the nearest hundredth, we get 1.97, and that's exactly what the standard deviation of our X bars was. The standard deviation of all of our X bars was 1.97. And that's exactly equal to sigma, which is 6.22, divided by the square root of n, which was the square root of 10. All right? So we have now verified, or we have confirmed in this example, that the central limit theorem does seem to hold true for large enough sample sizes, for a large enough sample from the population. Okay? Like, subscribe, comment down below if you're enjoying these videos, if they're helping you to understand a little more about statistics and a little bit more about the formulas and the concepts that you're applying. And I'll see you in the next video.